So, hello everyone. Welcome to today's quantum spacetime seminar. We are very happy to have Ayan Mukhopadhyay from IIT Madras, who will tell us about generalized Clausius inequality, error tolerant memory, and quantum null energy conditions. Over to you, Ayan.
Am I audible?
Yeah, you are audible.
Okay. So thanks a lot for this kind invitation to this quantum spacetime seminar channel. I have been following many of the talks here. So what I will do today is to talk about some of the recent work I'm doing in this general direction of connecting quantum thermodynamics and many body systems. And the overall goal is to understand, have a deeper understanding of many body dynamics, and also understanding when fault tolerant quantum computation or some quantum engines are possible or not. So that's the overall aim of the subject. So the talk will be essentially based on these three papers. The first paper is to appear in physical PRL this month, and the other paper, based on the nice comments of the referees, we have also submitted. So we don't know, okay, we have to see our luck, and it's on the archive though. And then there are some upcoming works and results which we will talk about. The first paper is with Tanay and Pratik. Tanay is my student and Pratik is my postdoc. So they have done absolutely fantastic work in this thing. And then it has been joined Abhik, my another postdoc, who is shared with LPNS in Paris. He has joined, and then the two undergraduate students have also been involved here. One is from IIT Bombay. He's now in the Dalibard group in ENS, and Rishi is a final year undergraduate in our department, and Suresh and his student also have joined us. The plan of the talk will be as follows. I will first give you a general introduction to quantum thermodynamics. It might be a very young and subject also, and maybe relatively unknown. Which is going to be the core of the basics, put up the basic framework that we are going to talk about. And then we will discuss the setup and tools, especially the holographic setup and the tools of quantum null energy condition that we will use. And then we will see that we have a generalized Clausius inequality. So Clausius inequality simply tells us the classic second law of thermodynamics, tells us that irreversible entropy production is always positive in any physical process. But here we will see that we get lower and upper bounds, both the lower bound and an upper bound. And already when I introduce, I will tell you why. And we will see in holographic systems, in many body systems. So previously, quantum thermodynamics people using results from quantum information theory showed that the lower and upper bound, the lower bound is simply postulated, the hypothesized. I mean, it has been shown it exists, but as you can see that it's not, nobody knows how to compute it. And the upper bound similarly is also very hard to compute. But what we show is that they do exist in many body systems. And and then we similarly show that there will be bounds and growth of entanglement. And then we will see, as a follow-up on this discussion, like in quantum thermodynamics literature, you could also talk about generalized Landau principle of erasure, which tells you that if you do some irreversible logical operation, there is also an irreversible entropy production, and it's generalized in quantum dynamics. And we will see also how this kind of things tells us how to protect from fast erasures and other fast errors. And I will also end with a summary and outlook, tell us that what new insights we can learn as we follow through this program. Okay, so let me now.
Can I ask?
Yes, please interrupt and ask. Yeah.
Regarding item 3, so this lower bound is related to the efficiency of the Carnot machine.
No. I'm just going to talk about it. So this will be actually in the introduction. It will be in my slide 2 or 3. Yeah. So I will be spending many slides on that. 2 slides at least. So I'll explain that. Yeah. So let me just talk about like why what is quantum thermodynamics? It's a very young subject. I mean, it doesn't go beyond so much back before 2016 or even 2010 maybe. So it's relatively young, and essentially the study is how thermodynamics generalized to finite and infinite dimensional quantum systems. But obviously most of literature is about finite dimensional quantum systems only, and infinite dimensional quantum systems is probably we are maybe the first people to even think about using holographic tools. So anyway, so it's the goal of this thing is to say, so any physical process is a quantum channel, of course, and not necessarily unitary evolution, but a CPTP map. And the essentially idea is to quantify resources like minimum amount of work, energy, information. That's also a new resource that you need to operate various quantum channels. And a very good review of it is in Chittambar and Gore from Review of Modern Physics. So I just highlight 3 topics before going into this irreversible entropy production, which will be. So one of this important thing is to understand that minimum work cost to prepare. So it's about a finite dimensional system. If you want to prepare a state, it can be shown that the minimum work cost that you need to prepare it, and also how much work you can extract from it, is related, can be given in terms of something called hypothesis testing relative entropy. It's a version of relative entropy. I don't want to go into it. So and then with respect to an appropriate Gibbs ensemble. So given the energy of the state, you could talk of a Gibbs ensemble with the same energy, and you compare you compute the hypothesis testing relative entropy that you can distinguish the state from the Gibbs ensemble, and that actually gives you the minimum work cost. So this result is due to Junger-Halpern, and so then you can also ask about like not only resource of energy but also resource of entanglement. Like if you want to have a teleportation quantum channel, you require non-local entanglement. How much of that you need to operate a channel? And also you can ask questions like the minimum initial entanglement that you need. So if you take a hot and cold system in classical thermodynamics and isolate them from rest of the universe, then heat can only flow from the hot to the cold system. But if this hot and cold system are initially entangled, and they're isolated from the environment, then the heat can also flow the other way. But there is no violation of second law because there's initial entanglement between the hot and cold system. So you can actually run it backwards. You can have this anomalous heat flow also possible with the entanglement. So if you, with some quantum resources, you can actually make some impossible things also work. Which are impossible classically. So quantification of all of this is essentially quantum thermodynamics. So let me now talk about this generalized Clausius inequality, which Pushkal was asking. So let me first start. With this lower bound, I'll also show there's an upper bound. So the classical second law of thermodynamics simply tells you about the Clausius inequality, which tells you that the irreversible entropy production has to be positive or non-negative in any physical process. But if you take into account quantum dynamics, there will be both lower and upper bounds of this. To give you an example, so this is a work, I'll give you the reference in the next slide. So consider a closed system and let the system initially be at thermal states, and beta is the inverse temperature. And let us drive this thermal state by a time-dependent Hamiltonian. So you can think that the Hamiltonian has some parameter, lambda, becomes a function of time. Then you can define the irreversible entropy production in terms of the expectation value of the work times inverse temperature minus delta F. And this delta F is essentially equilibrium work. And how to compute it is that you know the Hamiltonian, you know the initial and final Hamiltonian, which evolves as a function of time. And then you compute the Gibbs ensemble with respect to this Hamiltonians, define the free energy, and that gives you the definition of equilibrium work. And this is a work that you actually get, and an expectation value of the work is simply, you take the Hamiltonian at time tau, it has energy spectrum EM, and you take the transition probability from initial state to the final state with this energy. And then you also take into account the initial probability that you are in this initial state. So there has to be some Z inverse, which I forgot to write, which normalizes initial probability distribution. And then this would be the expectation value of the work. And if you think of a probability distribution of work is given by a similar expression, then you take that W minus this value, the change in energy is the work. And then you compute the probability by a product of the transition probability and the initial probability that it's in this energy state. So, and then with this, you can also get this delta. So your delta S irreversible, you can also write a similar expression for a probability distribution for that. And with this definition, you can show that the expectation value of minus delta S irreversible is actually identity. This is one very important. This is called a fluctuation relation. So it's one interesting result. So this is the definition of the irreversible entropy production. Very straightforward. So what you can show that you can put a lower bound on this delta irreversible, and this is based on existence of distance measure. So it depends on what distance measure you choose. So your distance measure has to satisfy the following requirements. It has to be invariant under unitary transformations, it has symmetric, and it has to contract under CPTP map. So with unitary, if the transformation is exactly unitary, then the distance doesn't change. If non-unitary, it's but a CPTP map, then it contracts. It becomes smaller. So one example of such a distance measure is the Buret's length, and this is defined in terms of the fidelity or quantum fidelity. This is one example. And given such a distance measure, you can show the relative entropy is bounded from below. And this basically gives you, because you can compute you can write an expression for the irreversible entropy in terms of relative entropy. And then you can get this. And essentially it's given by the Buret's length squared between the non-equilibrium state that you are getting and the corresponding equilibrium state with respect to the Hamiltonian at time tau. And it has to be greater than equal to this. Of course, this normalization 8 by pi square depends on the choice of Buret's length. If you choose some another distance measure, you will get some another normalization. You will always get some lower bound based on this. But it's not known which distance measure can put the tightest bound. So it's because all possible such metrics are not classified. So it's not known actually what the lower bound is. But given a certain distance measure, you can find a lower bound for the irreversible entropy production. Okay, Pushkal, so you have some, maybe this answers your question.
Yeah, I think Gautam asked the question, but Shiraz wants to ask a question, but Shiraz, we can't hear you. Okay, maybe you can go on.
Yeah, maybe I can ask a question on.
Yes, definitely.
So, yeah. So first of all, if you go back to the previous slide, then So are you going from an equilibrium to an equilibrium through an adiabatically slow process? Is that what you have in mind?
No. So this time-dependent Hamiltonian could be a quench, very fast process, or it can be an arbitrary time-dependent process. So initially you start from a thermal state, but then the Hamiltonian changes with time. And then to compute the equilibrium work, you simply take the Gibbs ensemble that you construct from the instantaneous Hamiltonian.
But are you reaching an equilibrium also finally or not?
No. It's a general it's a rho of tau is a general non-equilibrium state. It is, you have to compute it using some dynamics, whatever the dynamics is.
Okay, and okay, all right. So I'm a little confused about this last equality on the previous slide, which is the, so if delta S has a lower bound, which means that delta S is necessarily positive, then, and this is a delta S is the random.
Sorry, it's the expectation value of delta S. I should have written as an expectation value. So this is so you say that this otherwise it should delta S beta without the expectation value W minus delta F. So this what I mean is, sorry. Yeah, I should have written to be more correct here. It's expectation value. Yes.
I see. Okay. Delta S expectation value is something necessarily positive, but it's a random variable, so that it goes okay. So all right. It's a bit unintuitive. The last that equality about exponential of minus delta S, but you were saying it's true. Somehow it can be proved.
Oh yeah. This is a very important. There's a classical version of it called I forgot the exact name. It's called a fluctuation relation. It's related to Jarzynski inequality and all, but is a So it's a very famous relation, but it's also true with this definition of irreversible entropy. It's also true in the quantum dynamics.
Okay. Thank you.
I have a question.
Yes.
So I suppose you are going to elucidate upon this later, but what are some of the physical systems that in which such time-dependent Hamiltonians are applicable?
Well, I think for the moment, it's a very general closed system. I mean, we are always thinking in the context of a finite dimensional system. I mean, unless I specify otherwise. So most of this work, I mean, most of the work that has been done, all these theorems that have been proven are in the context of finite dimensional systems. In finite dimensional systems, there are a lot of subtleties, of course, so one has to redo. Yeah.
And what is an example of a finite dimensional system?
Like a one qubit for a one spin half, for example. That would be a simplest example.
And what would thermodynamics or statistical mechanics kind of mean for such a system?
Yeah, that's the whole point. That's why we have to give this definitions, right, of work and free energy. So of course, so these are the definitions that we have to give. And the whole point of this quantum thermodynamics is to generalize usual thermodynamics to this context. And so you have to follow these definitions, and then these are the definitions. Then.
Ayan, can you hear me?
Yes.
Hi. Very sorry, I came in late. Can you just once again say the definition of this S irreducible, please?
Oh, so it is the work, right?
Yes.
And the work
done in going from where to where? In what process?
Oh, so you start from a thermal state.
Yes.
And then you drive the system by time-dependent Hamiltonian, where some parameter is a function of tau. And then you define work like this. So if you have, so in general, of course, you will get a non-equilibrium state as we evolve in time. But then the irreversible entropy is defined as beta times, okay, if you think of a random variable, I should have put an expectation value on the left-hand side, sorry.
Yes.
So, but if you don't put an expectation value, then W will also not have an expectation value. So it's beta times W minus delta F. And W is simply the change in the energy.
What is, beta is the initial temperature? Inverse of the initial temperature?
Yeah, exactly. It's initial inverse of the initial temperature. Delta F is the equilibrium work that you compute from this time instantaneous Hamiltonian. So you compute the Gibbs ensemble that you get from the instantaneous Hamiltonian after time tau, and that gives you the equilibrium work, the change in the free energy, essentially.
I see. So delta F is the following. It's the difference in free energies between equilibrium and equilibrium.
Exactly.
I see.
No, yeah. Thank you. Yeah. And this is a random variable. Yeah.
No, wait. So are you going from equilibrium to equilibrium or not?
No. We are not going from equilibrium to equilibrium, but delta F is computed by assuming that your final state is equilibrium, and that gives you the equilibrium work. So it's a change in the free energy if your final state would have been equilibrium. Right. But of course, you have a non-equilibrium state, and so you have a non-equilibrium state, and you have to compute the work done from the non-equilibrium state. Okay?
So is it like that the time dependence has become so slow that you can use adiabatic approximation, or
No.
Sorry, I'm confused about.
Yeah.
No. You're not using adiabatic approach. It's a very general result. So
okay.
Your
so
rho could be an arbitrary.
What is EM tau? Is it like the spectrum of the instantaneous Hamiltonian?
Yes, exactly.
What has that got to do with the real time dependent eigenvalue? I mean, what I mean to say is that, the spectrum of the instantaneous Hamiltonian may have nothing to do with the solution of the time dependent Schrodinger equation.
Yeah. So this is the way you do it. So this is the way to, you can think of it just simply the expectation value of the energy, and you can also write it in that way. So this is just a common way of writing it. So this probability, because you write it in terms of path integrals. So this is a transition probability from initial state, eigenstate, to an energy eigenstate. But this transition probability is conditioned by your final state, whatever it is. And this depends on the dynamics, right? This depends on what kind of dynamics you're having. So this is a very general way of writing it. It depends on whatever dynamical process you are doing, and so yeah.
So will you give a derivation of
Shiraz,
that
you were
formula?
saying, Shiraz, you were saying something, so which probably I.
I think there are two quantities. The first quantity is just dependent on this delta F is just dependent on the parameters of the initial and final Hamiltonian.
Okay.
Yes.
You take some coupling constants and you've got some path and coupling constant as a function of time. Delta F is just what would the free energy have been had you been at the final values of the coupling minus what the free energy is at the initial values of the coupling, independent of the path and so on. Just the thermodynamics.
Yes, exactly.
Whereas W itself is path dependent. It cares about how you've changed your amplitude. Okay, and wait, there's one thing here, Ayan, there's a dimensional issue. I mean, I think of F as a quantity of dimension energy. How come the right-hand side is one quantity of dimension energy and another one of dimension entropy?
Wait a second. So T delta S has the same dimension as energy, right?
Where is T delta S?
So beta is 1 by T. So it goes, if you think it goes here, that
left-hand side is entropy. Right-hand side, the first term is T is work by temperature. The second term has just work, right?
Oh, wait. Yeah, could be that.
You wanted the beta, you wanted T delta S on the left-hand side?
I think, yeah, maybe there's a beta overall. Yes, you're right.
Yeah, and beta multiplies both of them on the right.
Okay.
Yeah, beta should multiply both of them. So that's the typo. Thanks. Yeah.
Okay, thank you.
Yeah. Thanks, Tanay, also. Yeah.
Are you going to give a derivation of that formula?
No, that's not the no. As I said, you can go to this reference, see the derivation.
No, not
so
this. Go to the previous slide. This expectation value of the work. Are you going to give a derivation of that from fundamental principles?
Well, if you believe this is, I don't know. This is probably very straightforward. There is no derivation needed. Right? So this is simply telling you that if it's you are just simply writing it in terms of the probability that you reach this final state, dependent on the process, and you start from an energy eigenstate. So this is very obvious, right? I don't see why what more derivation you will require here, because this is sort of a very straightforward. It's a straightforward formula in that sense. Okay.
Ayan, just to understand, is there a way to write this irreversible entropy in terms of some von Neumann entropies or relative entropies or something?
Yes, indeed, it is possible. So I didn't give this formula. So one way to see it is actually there are two. Yeah, I should have included that perhaps, but anyway, you can write it in terms of the energy increase in the entropy of the system plus increase in the entropy of the environment plus the relative entropy between the initial environment margin. So initial reduced density matrix of the environment and initial final reduced. So these all goes into this thing, because then you use some result. I should have also cited something that proves that relative entropy is bounded by such distance measures, and this leads to this formula. Yeah.
I see. Thank you, sir.
Okay. Maybe I can go ahead because so anyway, so maybe you can let me go ahead with this, because so far I was talking of a closed quantum system and it's very abstract proof. But if you want, but for the case of an open quantum system with Markovian dynamics, there is a more intuitive result. It was given very recently, actually last year. It's also a PRL paper. So as you know, this is given by some sort of a Lindblad equation where you take the environment to be very fast and not very affected. The coupling is weak, so the energy eigenstates of the environment are not changed by the coupling. And also you assume that this is basically saying that at every point of evolution, the full system can be factorized to a good approximation. So you get the Lindblad dynamics in terms of so-called jump operators. I think this is sort of well known. So these are like the initial, like you take a free Hamiltonian, these are like the AK, the creation annihilation kind of operators. So anyway, for these kind of dynamics, you can show that at the end expectation value of this irreversible should be bounded by this object. So relative entropy between two things. So one is if you would have only unitary evolution by this term alone, the state that you would have got, versus the actual non-equilibrium state that you get from the full dissipative dynamics. And this is not exactly the relative entropy. This is basically the entropy with rho. So this is basically is defined like this. So you take pi as a projector onto the eigenbasis of rho, and then you take this. This is standard. So this gives you the what I call SM. There's some name for this also. I forgot. So the lower bound is in this basically distance between unitary and dissipative evolution. So that's the content of this irreversible entropy. So this becomes a little bit more intuitive in the context of an open Markovian quantum system. So this is what I wanted to say for the lower bound. And now I can talk about the upper bound. Now, how does an upper bound also come from a rate of irreversible entropy production? And this actually comes from the minimum time that you require to go from a state rho naught to rho tau. And this minimum time is actually bounded. So this actually comes effectively from the uncertainty principle that if you have to take a pure state and go to an orthogonal state, the minimum time that you need to go from a pure state to its orthogonal state will be bounded by the spread in the energy of the initial state. So E0 and delta E0 average energy and the spread of the energy. And then you can again show that they are bounded by the Buras distance, a much more refinement of this. And this result might be known to many people who work on quantum complexity. So this from 2003 is a very celebrated result that tau min is, but this assumes that your Hamiltonian is time independent. To generalize it to irreversible entropy production, you need actually, and for the closed system evolution that I was talking about, you actually need to do a little bit more work, but you can show that similarly, that the irreversible entropy production is then bounded by tau times this thing. And this is the inverse of this minimum time. And then there is some prefactor. So this is how and this is related to something called Bremerman-Bekenstein bound, because I'm running short of time. Maybe I skip it. So in some limit, it reduces to some known bound from 1981. So this is a very nice result that you get from, there's an upper bound also.
Ayan, can I ask a question?
Yeah. Sure.
So this is basically a generalization of the Margolis-Levitin bound?
I really don't know what is that. I'm sorry.
So that's basically the statement that a quantum system has a maximum rate of dynamical evolution.
Yeah, sort of. It's a relaxation. There's similar bounds also in relaxation times.
No, not relaxation, not relaxation, evolution.
Okay, I don't know about that. So maybe I cannot comment. Okay, so because I don't know what precisely that is, I can recall. Okay, so similarly, there is people have used similar methods to derive generalization of Landau principle. Now, what the classical Landau principle says, it says that if you do any irreversible logical operation, it must accompany irreversible entropy production, and there will be irreversible energy transfer from information carrying degrees of freedom to non-information carrying degrees of freedom. And this was analyzed in quantum dynamics using very similar kind of setups. But here what you do is that you take a quantum system, and then it's finite dimensional quantum system again. You couple it to a bath, which has a temperature T, and then some heat flows into the bath. So the sign is positive when heat is flowing into the bath. And then you show that actually typically in this way of erasing, the entropy of the system actually decreases, because what happens is that it's a many-to-one map. So whatever state you start from, the final state is fixed. That is what you mean by erasure. So the entropy of the system actually decreases while positive heat flows. So this actually should be greater than equal to 0, according to in classical, and you can actually saturate the bound if you do it very slowly. But in quantum dynamics, you see that you get something positive on the right-hand side. And this has to do with the generation.
Isn't there a dimensionality problem in this equation? On the left-hand side, you have entropy. On the right-hand side, you have temperature times entropy.
Yeah, again, that's good. I mean, wait a second. No, there is no problem because the entropy is dimensionless, right? Oh, sorry.
I mean the
total entropy, the entropy density is not, but the von Neumann entropy is dimensionless.
No, the first two equalities. In the first two equalities, you have DS and you have DS.
Yeah, sorry. Yeah, I have to recall. Yeah, this is sorry, I haven't. So Yeah, of course, I choose KB and H bar to 1 all throughout this talk. And that too. Okay. Anyway, sorry for that. Yeah. I think this is dimensionally correct because it has acceleration. But right-hand side, I have to think. I'm not sure. But okay, the main point that I wanted to say is that there is something on the right-hand side, and that depends on the system size, but it goes size of the bath, and it goes to 0 very slowly with log. We will see something similar, but where we are not talking about the system of size of the system, but we are talking about if what happens if there is a very fast erasure. So we'll talk about that.
Hi,
so
essentially, can I ask a question if it's not too much?
Yeah, okay.
How do you distinguish between degrees of freedom which carry information and those which don't?
Well, it will be in principle in the quantum system. You can easily say that it's what you call the encoding, what is it called, the code subspace where you are encoding information.
Okay.
Versus something there.
Okay, thanks.
Okay, so in this equation, I mean, there is a violation of dimensionality in all the 3 terms, right?
Okay, sorry for that. I mean, I don't know whether there is a violation.
No,
the
the first equality is just Q by T plus delta S equal to delta S irreversible.
Yeah, so the T should be under the Q.
Yeah, I think so. Sorry for that. There should be a T here. There should be T times delta. So, yeah. Okay, so our goals would be, sorry for all of that. So, okay, so so our goals are as follows. So show that the upper and lower bounds on irreversible entropy production do actually exist in many body systems. So actually what we will show that if you employ the quantum null energy condition, this upper and lower bounds should exist, and not only hypothetically, but actually, because if you go below and above the bound, then you will violate the quantum null energy condition. And we can compute these bounds explicitly and also study similar bounds on rate of growth of entanglement, which has not been considered so far in the usual quantum thermodynamics literature. Then, of course, we study generalized Landau principle and find out if quantum thermodynamics can give insight into how you can construct such error-tolerant memory. And we can also see if we can protect against multiple faults actually simultaneously. And there's some other things that we were going to talk about. So maybe I skip because of lack of time. So our approach would be essentially study holographic systems in general way without committing to any explicit form of bulk matter. And we will restrict to quenches where you have inhomogeneous energy momentum flow from infinite energy memoryless path, and use the quantum energy condition to address this question. Okay, so this is sort of a rough introduction to this, and now I start what we have done. So the tool that we were going to use is the quantum null energy condition, which probably is known to many people, but let me still review it. Again, I'm using units where h bar is 1. So then the quantum null energy condition, a 2-dimensional CFT takes this form where the non-zero components of the energy quantum tensor are bounded by derivatives of the entanglement entropy. So the way it happens is that suppose this is a point where you are computing the null energy condition, and then you take any interval of any length that ends at that point, then move that point in either x plus or x minus in the left or right null direction. And you will get a new entanglement entropy, computes its derivative with respect to this displacement, second derivative and first derivative. Then you see that, that there is a bound on the energy density in terms of the derivatives of the. So if you, in the classical null energy condition, simply means that T plus plus and T minus minus will be positive. But in the quantum null energy condition, they need not be positive. And in fact, this object on right-hand side can also be positive. So in that case, you get a stricter bound. So it cannot be zero in that case. So you get whatever it is, you get some bound on right-hand side, which only is relevant when you have quantum h bar not equal to 0.
Again, you have some dimensionality problems in this equation.
With h bar set to 1. Here I set h bar to 1. Okay.
Yeah, but T plus plus is...
No, here there is no dimensionality problem. Entanglement entropy is dimensionless, and you have exactly the right dimension here.
No, what is T? It's just the energy momentum tensor, right?
Exactly. So this is certainly no problem with dimension here.
But energy momentum tensor is just the density of the energy, right?
So there is no problem with dimension here. This is dimension -2. This is dimension -2. This is dimension -2. So this is energy momentum tensor, right? So it is energy by volume, energy by length.
So how is it
Okay,
dimension?
so okay, maybe maybe I go on. Okay. So the general construction that we are going to do is as follows. We start from states where this is equal to 0. And these are essentially thermal states, or what are more generally called quantum equilibrium states. And these are those which has Virasoro hair on top of vacuum or thermal states. So that's sort of rough way to put it. I mean, I'll have more. So essentially the dual of these states are given by Barnard's geometries, and they saturate both equalities. So for any length of the interval, they saturate, you can show that Q plus minus 0 in these states. And this has been shown in this paper in 2019. And now we have to take, so all of these things that we are going to discuss can be understood by this kind of geometries. So you take one quantum equilibrium state, you are going to another one. And this is a geometry, time-dependent geometry that you have. So you have a mass, a time-dependent mass, and a time-dependent angular momentum here. And this metric satisfies Einstein's equations and with the bulk stress tensor. And the bulk stress tensor takes this form, where again, this Q and P are parameters, and these are given by this Ward identities in the bulk, or there's a constraints of Einstein's equation, or equivalent to Ward identities I will see in the boundary. So these are the constraints of Einstein's equation. So once you solve P and Q, you will be able to determine the bulk matter completely. And this is completely ignorant, or we don't commit to any form of bulk matter. So this particular bulk matter is actually conserved and traceless. So it's a null bulk matter in this metric. And that doesn't require to solve an equation, or irrespective of whether it is on shell or not, whether it satisfies this equation or not, this stress tensor is conserved and null. But then if you want to solve this equation, all that you need to do is to solve these two equations. That's it. But we are going to take a special, before taking a special limit. So in the case when Q and P are 0, these two equations simply imply that M and J are sum and difference of two chiral terms, which is the L plus and L minus. This is basically T plus plus, is basically T minus minus then. And these are general of the dual theory, and these are called quantum equilibrium states precisely, and can be classified by coadjoint orbits of the Virasoro group. And not all of them, but most of them are basically Virasoro hair on vacuum or thermal states. You have to make sure the exponentiation is proper, so that the exponentiation closes, and many others have more exotic interpretation. So, but we are not going to talk about very exotic stuff here. And what we see is that the QNIC inequalities for these states are saturated in all. So this is what I said in the beginning. So essentially now we can go from, suppose you take this to be localized in time and space or time, then you can go from one quantum equilibrium state to another. But what we are going to study or focus in this talk would be instantaneous quenches. So you start.
Just to understand. Yeah. Sorry, just to understand. Yeah. Are you saying that the QNEC is saturated whenever there's no bulk matter? Is that what you said, or did I misunderstand?
Yes. Yeah. Perfectly. Okay. Yeah, that's exactly what I meant. This QNEC is saturated
perfect.
whenever there is no bulk.
Good. Thank you. Yeah, thanks.
For any length of any interval, actually. Yeah, so now you can describe instantaneous quenches where you can go from one Barnard's geometry or one quantum equilibrium state. So there is one set of chiral functions to another set of chiral functions. And then your mass has a theta minus t and a theta t. So before t is equal to 0, you have this geometry. And after theta equal to 0, you have another one. And similarly, this is j. So it's exactly this form, but with two different functions at before t less than 0 and after t greater than 0. And then Q and P are completely determined by whatever initial and final states are. So it's completely irrelevant what makes up this bulk matter. It's simply given by the initial and final states. And you automatically satisfy Israel junction condition. And one of the things that you will see, if you say that the QNEC is not violated in dual theory, it implies that bulk matter satisfies the classical null energy condition. So, and the Israel junction conditions are satisfied automatically because ultimately they come from constraints. And if you satisfy constraints, then obviously Israel junction condition is also satisfied. Essentially, the bulk matter is now an inhomogeneous null shell. Once you substitute those Q and P, you will see the bulk matter has a delta of T. So it's the null shell, and where T is a null direction in the bulk, although time-like at the boundary. And this is a inhomogeneous null shell, whose form is completely determined by Israel junction conditions and the initial and final quantum equilibrium states. And there is nothing to worry. So all the examples that we'll look into will satisfy classical null energy. Bulk matter will satisfy classical null energy condition. So actually QNEC in the dual theory will automatically imply that. And this is actually saying that you, of course, should reproduce, if you lower the temperature, then you violate QNEC. So you have to actually have irreversible entropy production positive. And that makes the bulk matter satisfy classical null energy condition automatically. So holographic normalization of this geometry tells you that your T plus minus is again given by some initial value and goes to the final value. And del mu T mu is equal to F nu. And this is a boundary T mu, not the bulk stress tensor. This is a boundary dual stress tensor of the dual state. And this F nu is basically then the energy and momentum injection from the bath, infinite energy and non-reactive bath. So this is what it is. And the method that I don't want to go into technicalities, but the method we use, and basically we reproduce many very well-known known results in literature and go much beyond. It's a very elegant method. Is that the way you try to solve this or compute entanglement entropy and the quantum null energy condition is simply that you note that before and after the quench, you have essentially Barnard's geometry. So you can uniformize it. You can have two uniformization map to Poincare patch, and then you take and then when you glue them, so basically T is equal to 0 will be two hypersurfaces, sigma I, sigma F, because for each uniformization map you get two images, and the way you glue points of these two images is that you identify coordinates that are the same physical coordinates, small r and small x. So small r and small x are your physical coordinates, and Barnard's coordinates will be capital T, capital R, and capital X. So you have two Poincare coordinates, 2 Poincare patches, but these 2 points, but those points which will have the same physical coordinates should be identified. So that's the way you do that, and therefore you cut this root Akanagi geodesic into 3 arcs, and now but you can easily compute once if you know how to solve this intersection points, you can basically compute the entanglement entropy, and then of course its derivative also rather easily. So that's essentially the technique that we follow. So let me come to the results now. So what we do is as follows. So the simplest thing that you can do is to go from one thermal state to another thermal state. So in that case, you have a T plus plus and T minus minus are simply given by the respective right and left moving temperatures. The actual Hawking temperature is essentially the geometric mean, and the actual Hawking entropy is simply the sum of the two temperatures multiplied by C by 6. So this is very well-known results. And now you can look at how the quantum null energy condition looks and for a given length. So actually, because of symmetry, you can just take only one. So you can just, because there's spatial translation symmetry, you can just take the interval x greater than x equal to 0 to x is equal to L. And you can study both the Q plus and Q minus of the left endpoint. That will be equivalent to studying Q minus and Q plus of the right endpoint. So anyway, so you can do that and you find the following thing, that when you take the right moving thing, you see that as you increase the length, it becomes lower and lower uniformly and so for Q minus. So the strictest bound, if any, should come from the length of semi-infinite length, interval of semi-infinite length. And all of these results are analytic, actually. Sometimes it's very hard to write down. If you write down actual expressions, you cannot simplify them. It becomes too long. But I'll show you some actual expressions.
Just to make sure I'm understanding. Yeah. So you start in this example, you start with thermal equilibrium, and then you do an instantaneous quench. Is this right?
Exactly. So you inject energy and momentum.
And this is uniformly over the sphere or over the circle?
We don't have a sphere. It's an infinite length. So so we are in the Poincare patch.
Okay,
so
fine.
It's
uniformly over this R1? Your injection is uniform. And because the energy momentum just moves straight in, the quench is instantaneous, or it has a time scale associated with it?
Here it is instantaneous. So, I mean, this is a very classic thing people have studied for long, like I think start from beginning from Vijay Balasubramanian. So this is simply that, and Jan de Boer. So you simply take the ADS Vaidya, where you just you go from vacuum to a finite temperature instantaneously by shooting in some homogeneous null shell. So here what you do is that you go from arbitrary ADS Vaidya to, arbitrary BTZ to arbitrary BTZ.
Lovely. And and tell me again what you're plotting in your plots, please.
This is the Q plus and Q minus, which I just
just remind me what is Q plus and Q minus.
Okay, so good. So these are these expressions, but these are functions of time, because for t less than 0, these are 0 exactly for any length, as I said before. For t greater than 0, is discontinuous that t is equal to 0. Both Q plus minus, and then you will find that I simply plot this.
Sorry to be so stupid, but holographically I understand how you measure T plus plus. What is this S double prime entropy? How do you measure that holographically?
Okay, so you simply compute the Routh-Akanagi entropy using this method, and you displace one of the endpoints. So you can take, for example, x is equal to 0, x is equal to L. And you displace this point in the null directions and compute the entropy again, take the derivative.
Okay, now I understand. So that's why it's a function of the size. The T plus plus was not a function of the size, right? That was
the T plus plus is not a function of size. So this becomes a function of size, and the strictest bound will come from the infinite.
I see. So the shell is moving in, and because the shell is moving in, if you took a very small length, the whole Routh-Akanagi surface would be in the new temperature.
Exactly. So then it will not. Yeah.
If you took a very large length, most of the Routh-Akanagi surface would be in the old temperature, and if you were somewhere in between, it would be half. And that's what your diagram.
Yeah.
Okay. Thank you.
Exactly. So you see, it ends at some point. That's L by 2, because after L by 2, whatever L is, if you take L by 2, then for example, L is equal to 8,4. You will not intersect this doing surface at all.
And I'm sorry, remind me. And the expectation was that this Q, there was some expectation from QNEC that this Q plus was something. Why?
No, sorry. All that I was saying that before, as I said, if you look into these geometries, any Barnard's geometry, your Q plus minus will be 0 for any length. So before, for t less than 0, these are 0, Q plus minus. But for t greater than 0, there's a discontinuity.
Why are we probing Q plus? Please again, what are we trying to check?
So let me come to that. So basically, we are simply checking whether Q plus and Q minus is positive for all time or not for any length. But it's sufficient to check for the infinite.
Okay, and there was a theorem that it was always positive. That's what you're checking.
Exactly. So the theorem has been proved for 2D CFTs.
Okay,
so
thank you.
Yeah. So then,
the Barnard's matrix that I know, they are without matter. So is this some generalization of Barnard's matrix?
Exactly. So it's a highly generalized. So this matrix gives you enormous generalization of Barnard's matrix, where you go from arbitrary Barnard's to arbitrary Barnard's. And you can also do it slowly, right? Not only fast, like I'm saying. So these metrics are very general.
And then
extremely general metrics,
And there's some general matter as well.
There is very general matter, but it takes this specific form. So once you solve this water entities at the boundary, you can compute this.
I see.
I don't know whether it was known before, these kind of things.
So this is something that you have found, this generalized Madras matrix?
Yes.
Okay.
We have found it. Yeah.
The matter is always, in what you do, the matter is always infinitely thin shell?
In what we do, yes. But we can generalize this, of course. But for the moment,
then you would have to look at the matter equation of motion as well. If you
no. If they're not instantaneous? No, not really, because no, you don't have to, because you see that this is so this you can be totally blind, because this matter is conserved and is null in this metric, and irrespective of whether this metric satisfies Einstein's equations or not, this matter is something that is conserved and null in this metric. And then if you want to satisfy Einstein's equation, all that you need to do is satisfy these two equations.
Conserved and null. So usually if I have, let's say, I don't know, a photon moving in the space, energy momentum conservation is a consequence of the equation of motion, but does not imply the equation of motion.
Right, exactly. That's a very good point. I mean, so the analysis is basically whether such things are possible. Then what you're asking, whether you can implement it, right? So that's a second question. Okay. So we want to first study whether such things are allowed or not.
Okay.
And then, of course, how the physical.
But I think in the infinitely thin shell limit, the equations of motion sort of become irrelevant.
Yeah, exactly. Sure, they're not so relevant.
There you're safe. Yeah.
I see.
Yeah, there you're safe. Yeah. No, that's the comment I also make at the end. Yeah. Okay, if I get to the end. Okay.
So then it's an empty space Bernoulli's solution inside the shell and outside the shell.
Yeah, exactly. Yeah, and Israel junction conditions are satisfied. Yeah, Israel with this bulk matter, the Israel junction conditions are satisfied, and the matter satisfies null, classical null energy conditions, because you have to satisfy QNEC at the bottom. So that comes automatically.
Okay, but for fat shells, you have to know the metric inside as well. So okay.
Yeah, exactly. Yeah, for a fat shell, things are, you cannot be totally blind to matter. Yeah.
Could you go back to the expression for Q plus?
Which you mean the definition of Q plus or the expression?
Yeah. The formula for Q plus.
Yeah.
Yeah, this one. Yeah. So here, see, T plus plus is energy by L square, right? The dimension of T plus plus.
No, energy by L is not L squared. There is only two-dimensional CF. You have only one space. No, this equation is dimensionally correct. Don't worry.
How?
Okay. How? It's energy by length, so it's energy square.
Yeah. All quantities are mass dimension 2.
Yes.
A stress tensor in any quantum field theory is dimension of the space-time in mass dimension. So that's true.
And what is the dimension of entropy? It's
a dimensionless 0. Derivative has dimension 1. So if you have two derivatives, that has dimension 2. Both terms have two derivatives.
Okay. So these plots are actually made from analytic results, not numerical. Okay, but they're hard to write down. So let me give you one expression. So for example, if you start from some rotating BTZ and go to a final thermal state, which is non-rotating, so that you have mu plus final is all mu, and then you take the semi-infinite interval, you get these expressions. So these are rather non-intuitive, but one of the things you easily note from this formula is as follows: that suppose I start from the vacuum, suppose my mu plus I and mu minus I are 0, then both become 0. So for the semi-infinite interval, Q plus and Q minus are always 0 if you start from the vacuum and go to a non-rotating state for the semi-infinite interval. This is not true if you take a finite interval, which is very interesting because the quantum null energy conditions get saturated, although entanglement takes some time to thermalize, because entanglement entropy, or you take a finite size interval, that doesn't thermalize, that the density matrix will not thermalize until you reach time L by 2. It will not thermalize or be close to a thermal state. But here you see it thermalizes. So that is one interesting observation.
So anyway, sorry, you said Q plus and Q minus were both always 0?
Yeah. If you take mu plus and mu minus I to 0, of course, otherwise not. Because if you take mu plus and mu minus I to 0, then this is true.
Oh, sorry,
because because your numerator vanishes.
What was mu
your
plus
numerator
I?
vanishes?
Mu minus I.
This is the initial left and right moving temperature. and the final left and right moving temperatures are the same, and mu, which is equal to mu.
What is I in that?
I stands for initial. So let me.
Oh, I see.
This is a notation. So I is for initial, F is for final, and this is the left moving temperature. Minus, and the plus is the right moving temperature.
And can I understand the zero as follows? That because you're taking a very long interval, almost all of the Ryota-Kannage surface is in the old temperature, and so that the thermalization started happening doesn't matter for the S double prime and S prime terms.
Actually, well, this is a very good point. You're absolutely right. Actually, so what happens at very early time, S prime is 0, but S double prime is non-zero. At late times, it is S prime that is non-zero, but S double prime is 0. But together, they always conspire such that this remains exactly the T plus plus T minus minus.
Oh,
so that's really fascinating. Yeah.
Oh, so my wasn't correct. Okay, thank you.
Yeah. Okay, so now let us see when do you violate QNEC. So let me explain this. So now if you start from say a left moving temperature 0.75 and right moving temperature 1 in whatever
sorry, just to ask a quick question about the previous slide. If you had ignored the S prime squared term in Q plus and Q minus, then you wouldn't see the saturation. Is this right?
You wouldn't, exactly. You wouldn't see the saturation. So, yeah.
Okay, so then S prime squared term is important in this case.
It's very important in this particular thing. And yeah, you're right. Yeah.
Got it. Thank you.
Yeah, welcome. So now let us give this, you study this example where you have an initial rotating state and ask what are the things that okay, by the way, I will also want to say the following, that if you start from an initial vacuum state, you see that the only state that is allowed is a non-rotating state. Otherwise, you violate the QNEC. So that I forgot to write it down here for some reason. So that's one interesting thing. If you start from the vacuum, but if you start from a finite temperature state, whether it's rotating or not, you get something like this. So here, what I show is as follows. So this is the initial state that we're starting from. And then this is a change in the left moving temperature. This is change in the right moving temperature. Now, Clausius inequality will tell you that this, both the temperature and, so it should simply be positive, that's all. That's what Clausius inequality will tell you. But what the quantum null energy condition tells you, if you require the quantum QNEC remains positive for all times after the quench, for any arbitrary length, of course, the bounds come only from the infinite length because that gives you the strictest bounds. And then you have to be in the white region. So that's a statement. So you can see from this diagram, so if you look into the change in temperature, the change in entropy, they have to lie within this white region, and not the gray region. The gray region is excluded by something, we'll see. So for example, if you choose your final temperature to be something, you get a lower bound and an upper bound on the total entropy. Like here, the lower bound is the blue and the upper bound is the yellow. So that gives you the lower and upper bound of the irreversible entropy production for a final temperature. So this is the interesting, this is the result. And how do we get the result? So for that, you can completely do it analytically. So you just first see that Q plus and Q minus has to be non-zero just after the quench at T is equal to 0. And that gives you this relation. Unfortunately, I didn't write what is delta. But these expressions are not so important, actually. So all that so these are these black lines, which you can get completely analytically. So otherwise, you simply violate. Then what happens is that you see that for the Q plus, it's sufficient to ensure that the T is equal to 0. And the reason is that the Q plus always rises like this. But Q minus, although it is positive, at some time, after some time, it can become negative. It can cross 0 and then again, then saturate to some value, some final value. But it always decreases like this. Unless you start increasing the final temperature so that it becomes 0 or greater than 0 for all times. So that tells you this gray region. Again, this can be computed analytically, but in many cases, if you can solve for the intersection points at least. So, but then you have to keep raising it unless you go above this curve, this gray region, so that Q minus is also satisfied for all time. And this is the corresponding thing in the change in entropy. So this is the way we get these regions.
Sorry, I haven't understood that. So what are these axes here? So delta mu minus
delta T. Delta mu minus is the change in the left moving temperature divided by the initial left moving temperature.
Okay.
This is the change in the right moving temperature by the initial.
So what does it mean? What does it mean that, I mean, so if QNEC is violated in the gray region, why is that happening? Or is that saying that I can't set up that experiment?
Exactly. So this is a very non-intuitive thing, I think. I mean, so again, I think the only thing that we can do is to appeal to this quantum known results, and there should be lower and upper bounds. But to see it a little bit more intuitive way, that is something that I really can't say. Okay, maybe I can give you one answer to this question. So what we find is something very interesting, that whenever this transition is allowed, then Q plus always increases and Q minus always decreases monotonically with time. And otherwise this is not true in general. So it might be has to do with something that we don't, that is not understood. I mean, I don't have a much deeper understanding of this result than the fact that we actually compute and find such lowers and upper bound. So this is.
But is it possible that this has to do with the fact that the bulk matter violates some energy conditions in the bulk?
That's a very good question. That's a very good question. Actually, no. So actually, if your bulk matter that violates the classical null energy condition, then QNEC is automatically valid. And that's actually the statement of Clausius, the usual Clausius inequality. So if your usual Clausius inequality is violated, that means that the bulk matter doesn't satisfy classical null energy condition, then your QNEC is automatically violated at the bound. But the point is that you are getting something more than the usual Clausius inequality. So it's not only positive, but it also has a non-trivial lower bound and a non-trivial upper bound. That's the main point.
Yeah, so I was thinking the following. If I have gravity coupled to a scalar field, I could turn on a source for the scalar field over some time and choose the amplitude of that source to be whatever I want.
Yeah.
And so I would have thought I would have been able to create any jump in temperatures. So it surprises me that there's some bound on how big the jump in temperatures can be. If I've understood it right. So I probably understood it wrong.
Yes, that is correct. What you're saying is exactly correct. The question is about whether such things are physically realizable or not.
Einstein theory coupled to a minimally coupled scalar field, if you can get a good solution in that system, I would be surprised if it was violating some physical.
Yeah, you're right about it. No, that's a good. Yeah, that's a good point. So these results that we have. So if you do it adiabatically, I think it should be anything is possible, and I think then you will simply get. I think that's also what we expect from this quantum thermodynamics literature. That if you do it very, very slowly, then this upper and lower bounds simply reduce to. The upper bound goes to infinity and lower bound goes to 0.
So opposite limit of doing it extremely fast. Now, unless you're saying that it won't send a very thin shell, maybe it won't send a very thin shell. Maybe that's wrong. In 3 plus 1 dimensions, Shantani and I had looked at a similar question.
I know. Yeah.
And we found that when we made the boundary source very thin, the bulk source was also very thin. But there was some odd even business, so maybe it's different in 2 dimensions.
Yeah. No, this is something that we should understand better. I agree, and this is something that we are also trying to understand by some simulating real systems. So it's a good thing that we should understand this better. So
and in this case, these non-trivial upper bound and lower bound, is it important that you're including the S prime squared term?
Yes, I mean, absolutely. Because at late
what happens
time,
if I just look at the is the usual T plus minus S double prime that kind of quantity?
Well, if you at very late time, the S prime becomes very important. At early time, only S double prime is important because entanglement typically goes only quadratically at early time, so diffusive growth.
Right.
But at late time, you get ballistic.
Yeah, I'm wondering whether if I just look at T plus minus S double prime, whether that will not violate whether that will not be violated.
That I don't think will be violated because that is, you see, that is simply not violated because of the following reason, that this is positive definite, right? So it only so if it is so it gives a tighter constraint. So if it is greater than this, then
right.
greater than it.
Exactly. No, that's what I'm saying. So you're saying it's possible for Q plus, and I mean it's possible for this inequality to be violated while still preserving the fact that T plus plus is greater than S double prime, right?
Exactly. Yeah. Right. Yeah. That's
so is that what's happening in the gray regions? Just to understand.
I'm not sure though. Actually, this gray region happens at intermediate times. So what as I show, so this Q minus, what will happen is that it will cross 0 and then saturate to some negative value. And as you go above, this quickly rises and then it goes to 0 at infinite time. So it always remains positive. So when you are at the boundary of here, so because it's an intermediate time, so S prime is also important. So if it's very early time, then S double prime is all that matters. But if it's just a little bit later than the early time, then S prime also matters. So I'm not sure that with S double prime alone. So maybe with S double prime you get you will get something that is much higher than this. I don't know. Maybe. Yeah.
Oh, I was thinking that with the S prime squared term dropped, you won't get any QNEC violation. But okay, I may be misunderstanding. Sorry.
Yeah. No. I also don't. I think, but yeah, you might. But I think, but this lower bounds, this bound at T is equal to 0 probably comes from S double prime itself. So you're right. Probably it pushes down and you simply becomes this. Yeah.
Yeah. That's what I was right. But okay. Yeah. Please go on. Thank you.
Okay, so at infinite time, then Q minus and Q plus has this behavior and they are monotonic. And what we generally find is that no energy momentum excitation leaves an interval. Then Q plus and Q minus is always monotonic. Q plus increases and Q minus decreases. Okay, there's some observations. And maybe I can skip fast and go to, so you can also bound growth of entanglement. Be very, very quick with this section and then ask you how much time I have. Well, let me finish this section. So
we are generally flexible with time, so you can take a little longer.
Okay, but still I don't want to exceed time unnecessarily. So, okay, so what happens is that if you take entanglement growth, you see that for a given region, you have some diffusive growth, then it becomes almost ballistic, and then it saturates. And there are some very classic papers by Hong Liu, Takayanagi and Mukund. So all of this actually gives you one. So they have studied this transition from vacuum to BTZ to depth. And so all these things are known analytically. So what is the diffusive coefficient D of S? You know this quasi-linear growth very well. And you can also show that at exactly at time L is equal to 2, L by 2, there's something called the horizon time where the root where the geodesic is entirely in the final geometry. And therefore it is equilibrates. And then you have equilibration with an exponent, which is 3 by 2. So all of this is very well known. So what we first do is that we find that we have analytic results now. For arbitrary BTZ to arbitrary BTZ transitions, we show the saturation time is always L by 2. And this is something that we can show analytically by the cut and glue method, which I just mentioned. We also have been able to show analytically that saturation exponent always 3 by 2. And then you can also compute this diffusive growth coefficient D of S at early time. And this is essentially, again, an analytic result that you can compute. So these are very new results that was not known in literature before. And then if you take this order of limit, you take L goes to infinity first, and then T goes to infinity. So in that case, you just simply get linear ballistic growth. And this is rather simple, which you can show. And this ballistic growth of entanglement happens at the speed Vs, and then it grows, of course, with time t linearly. And this Vs is twice of the final entropy density minus the initial entropy density. So this has dimension of length, or 1 over length, sorry. It's a dimension of 1 over length, entropy density. So what happens is, I think some similar result was shown by Gautam in one of his very, very nice papers, I think from which year. But in the context of a thermophile double, he was studying some similar process, and he found a similar result of growth, linear growth with this particular. But this can be easily understood in this way, that what is happening, you take an interval, then entanglement is spreading at speed of light from both ends. And then if you take time t, then an interval of length 2 times t has become almost thermal, exponentially close to thermal. And because if the intervals are sufficiently large length, then entanglement entropy is simply the thermal entropy density times the length. So therefore, the growth of entanglement will simply be twice SF minus SI times the length, which is 2t. So this gives you the result. So that's a very easy way to understand it, but it's something we can show analytically. And just like you have bounds now, so okay, so now you can easily see, because we already bound the change in entropy, both from up and below. That's what I showed here. For a final temperature, you have bounds like this. So it automatically implies that your Vs is bounded from both above and below. But you can also show that this diffusive growth coefficient, this analytic result that we had, is also bounded given those bounds on the final entropy. And this is what you find for a final temperature, for initial temperature, initial entropy, and for a final temperature, the blue is the lower bound, the orange is the upper bound on this diffusive. So that actually finishes this part. And I think if I have 15 more minutes, I can finish rest of the talk. Of course, unless there are more questions here. Is that okay?
Yeah, that's okay.
All right, thanks a lot. Okay, so the next thing that I'm going to is Landau erasure principle and erasure tolerant quantum memory. That's another application of this thing. So the first, before going there, I would have a small interlude and tell you a no-go theorem. So the no-go theorem is that it is not possible to have quantum memory which doesn't need any active error correction in 2D if you encode the memory based on stabilizer codes. So all of these details are not important. You just simply remember that you have the toric code, and basically in toric code you have 4 ground states on a torus, and what you do is that you can store a qubit in this so you can store 2 logical qubits in this 4 degenerate ground states, and what essentially you need to be able to have store memory without need of active error correction is that the energy barrier between the ground states will scale with the system size and go to infinity. That's like usually happens. But you know that there's a Marmin-Wagner theorem for 2-dimensional systems, 1 plus 1 dimensional systems, which tells you that local symmetry breaking is not possible. This is somewhat a similar theorem for topological order. And this tells you that the energy barriers between ground states for Hamiltonians for which stabilizer codes work, like toric code, do not scale with the system size. So as a result, if you take a topological order parameter and it decays practically very fast at finite temperature, even when the temperature is 1 order smaller than the barrier height. So this basically doesn't work. So you cannot use stabilizer codes. So there are there's a huge literature of how to circumvent this no-go result and go beyond it. So let us try something in 2D QFTs, and the idea is very simple. So what we do, we study a new kind of encoding, not based on stabilizer codes, but as follows. So what we do, we are trying to encode a qubit into a quantum equilibrium state, or some Virasoro hair on top of some finite temperature state. And the way we do it is as follows. So you have a memory at finite temperature. You need to study memory at finite temperature. So what we do is as follows. So every qubit lives on a block sphere. You project it on the Euclidean plane by stereographic projection, and then we do Lorentzian continuation. So now what we do at that point where we have this projection, we create 2 excitations, and both excitations are same. One moves left, one moves right, the eternal excitations. And this gives you a quantum equilibrium state or a Bernoulli's geometry. And this is something that you can create by unitary conformal transformation on a finite temperature background. And this f of x then has the property that it has, at mod x goes to plus minus infinity, it becomes d squared. And otherwise, it's a lump that has some sort of lumpish, something like this, diagram that I show, something like this, for example. So it can also violate, so it can violate classical non-energy condition, but not the quantum non-energy condition, of course. That's fine. So we have something like this. And yeah, so that is how you create. And this qubit can be then decoded simply by finding out where the excitations overlap. So these are eternal. So suppose I don't erase them, these are eternal excitations. And I measure the energy density T00 at some moment of time. I find these two lumps which are equal, and they will meet at some point because and I find where they will meet. I can compute it, and with that I can decode what is a qubit. Then I do the stereographic projection back on the block sphere, and that's how I decode it. So that's kind of an encoding that I'm using. And let's see how you can practically do it. Is that you choose this f of x using some kind of uniformization map on the boundary. So this is this sort of anomalous transformation of the stress tensor, and this because you have finite temperature background. This plus so this comes from the composition of the Schwarzian. So there's a I don't want to go into detail. If you don't want to put plus wx, you can put a tan h here also, if you want. So okay, anyway, and w of x is essentially Lorentzian plus some constant.
Yeah. Hi, just a quick question. Is this encoding isometric?
Well, it's on the top of a finite temperature background. So yeah, I don't know whether. Yeah, I don't know whether I don't know the answer actually. So Tanay, can you?
Maybe a simpler question: If I consider a superposition of two qubit states.
Yeah, no, it's not like that. Yeah, it's not like that. Yeah. It's not like. Yeah, you're right. It's yeah. So yeah, if you have to super
non-standard way. Yeah.
It's a very non-standard way. Exactly. Okay. Very non-standard way.
Thank you.
So the entanglement entropy for an interval, if you look into such a thing, if you take any entanglement entropy for this quantum equilibrium state, and L is much larger than B, and B is, so this is just one of the examples. So B is the localization length, but you can have many such examples. So all that you need is a lump or some kind of Lorentzian or some function plus some constant. The constant gives you the finite temperature background. Okay, and so if you look at the entanglement entropy, it will be thermal for a sufficiently large plus something S info. And this S info can be then interpreted as number of encoding qubits, that the number of encoding qubits for this logical one qubit. And it scales with the central chart, so it can be very, very large. And then there'll be small correction. So this is sort of the interpretation. And B is the length scale over which, because if you take L greater than or equal to B, you will get this result. So B is the length scale over which this information or encoding qubits are localized. So that's sort of interpretation. And the way we do the erasure is very simple. We go again from one quantum equilibrium state to another quantum equilibrium state exactly by the same metric and same procedure that I discussed earlier. So, but now there is no angular momentum injection, you have only mass or energy injection, and you go from this initial quantum equilibrium state to something that has only a finite temperature and is non-rotating. So it's like this. So then you can study the entanglement entropy of two intervals. So by symmetry, they are the same, and Q plus of one is related to Q minus of the other, and blah, blah. So it's enough to study only one of these intervals. And again, you see the quantum null energy condition automatically implies classical null energy condition for the bulk matter, and all the same observations that I made earlier will go through. So now let us see entanglement growth. If you take a semi-infinite interval s greater than or equal to x0, so this is the initial growth of diffusive coefficient. And just like we saw here, the diffusive coefficient always grows with the length. So it's sufficient to look into the infinite length limit. For example, if you want to now this diffusion growth has to be positive. And just from this, you could say that there should be a generalized Landau principle. Why is generalized? So here you see that the change in the temperature from the initial background temperature to the final temperature has to be equal to the maximum of this W of x minus Ti by 2 pi. So where W of x could be any W of x, as far as we have checked, any W of x of this type, where you have some lump plus finite. And this D by pi is the Ti actually. So you just take the lump actually, the maximum of the lump. So that will give you this result. And so this is a plot of the L plus L minus. It's a very long expression for example, the Lorentzian choice, and this is how dx0. So it's not symmetric because your interval is like this, x greater than or equal to x0. So it breaks the symmetry once you choose an interval because it's either to the right or to the left. So it is some asymmetric shape. So that's how this plot looks for the Lorentzian case. But if you study the quantum null energy condition, if you say that q plus minus t has to be greater than 0, again, the bound comes from the semi-infinite interval. So you see that you get exactly twice of this. In the limit, when the number of encoding qubits are very large and the localization length b is finite. So you get this very nice result. And why is a generalized Landau principle? Because Landau principle simply tells you the right-hand side is greater than or equal to 0, because here you do not put any heat inside the environment. All the non-information degrees of carrying degrees of freedom are inside the system, and you are simply heating the system. So it simply tells you that Tf minus Ti has to be greater than or equal to 0. But you find that it is not only greater than or equal to 0, but it has a non-trivial lower bound, which is given by the maximum of this W of x, this encoding map, in the limit when the number of encoding qubits is large and they localized over a finite length b. So that's a very beautiful general result that we have found analytically. But now I'm going to tell what happens if S info is not large, because that's not so interesting, because practically you would not like to encode with infinite number of qubits. So we have to understand it better. So now here comes some very, very surprising result. And I can try to give you some intuitive feeling of it, why this is correct. So what you see is that for a finite amount of encoding qubits, if you choose your encode, if you choose the b, the encoding length or the localization length sufficiently small, that is, if b should be less than or equal to bc, then so of course if you have zero temperature background, this bc is infinite, but for a finite temperature background, you'll see that if it is less than this critical length, then you cannot, this QNEC completely forbids the fast eraser process. So if your b is smaller than this, and this is your number of encoding qubits, you're completely protected against fast erasure. It's completely impossible physically to it. So that's very surprising. And but this is not so surprising, of course, here, because if you have no encoding qubits, of course, the deletion should be possible, and show this localization length should go to 0, because it should not put any constraint. Now, if you have a large number of encoding qubits, you go back to this result. And again, this does not depend on any localization length. It's completely independent of localization length. And therefore, you also expect that this localization length should go to 0 when your number of encoding qubits is very, very large, according to this formula, which doesn't depend on the localization length. Therefore, you automatically see that in the middle, it could be some non-trivial behavior like this. So that is basically plain. It looks non-intuitive, but you think in this way, it becomes intuitive, sort of, why you can have such weird behavior. And you see that the maximum is occurring at when S info is of the order of C by 6. So there you get the maximum localization length, or so it's basically optimal number of qubits that you should use to encode, because then you can squeeze them over a larger length scale, and then you can protect against faster deletion. Otherwise, you have to squeeze them over tighter and tighter length scales, and then only you get protection. So this is very surprising. And what does it imply? So this is what we studied. This is the result that we get for a large number of encoding qubits. But when encoding qubits are finite, this is what you get. And this delta is the minimal temperature that you should need, the dimensionless temperature that you need in order for the QNEC to be non-violated and deletion to be possible. And this is the function of the localization length. So when localization length is larger than these values, then of course, you get something like this. You get a continuous curve. And at very large S info, it will rise linearly. And this linear rise is simply given by this formula. It is 3 times S info by 3 pi square b. So it's simply given by this linear formula. So that's, and this is universal. And this is independent of localization length. Because independent localization length, all things should converge to the same curve at very large S info. Now, if you keep decreasing b below this, then you see that if I take something like this, maybe I annotate here. So suppose I take something like this, some localization length like this, and then you see that there are 2 values of S info between which if I keep my S info, it's impossible to delete. So there will be some minimal and some maximal value of S info for which deletion will be impossible, because if I have to go below this for the deletion to be possible. And so therefore, so that is exactly what you see. So that's exactly what you see in this curve. I have to delete it. Again, I have to do annotate it. Sorry. Okay, so now you see that, so this is the minimal and final value between which the minimal temperature goes to infinity. And that happens for this critical, if you go below these critical values. And this, so if you go below this 0.04 or something, you will see that this non-triviality emerge. Otherwise, you will not have any. But the point is that normally you don't require infinite temperature for deletion, because your ambient temperature is something. So TF is basically, say, the room temperature, 300 Kelvin. And suppose your quantum memory is operating at finite temperature, 50 Kelvin. Then you only need to see what protects you if your TF is only 300 Kelvin. And to see that, again, you have to look, you have to put, sorry, you have to put delta, you have to compute delta like this, 300 minus 50 by 50. So 250 by 50 is 5, your delta is 5. So you take delta is equal to 5, and you see which curve passes through it, which value of VTI will pass through this thing, and what is the S-info that you need. So what is for a given S-info. So suppose you find C is equal to 100, and then you see what value of B you need so that the curve will pass through it. So you find that your BC is only 2 micrometer, which is quite realistic. So basically you have to squeeze, squeeze only on your information only over, so it will be like 1 qubit per atom or something that you need. So it's not too much squeezing and it's realistic, and over 2 micrometer, and that's all that you need for protection. So that's some very realistic values. And you can also see that certain kind of, all the shift errors also protected by similar squeezing. If you squeeze your information sufficiently well. So this now requires you to, this is shift errors in which what is happening is that you have these lumps and the center of the lumps are shifting. So then it means that you cannot reconstruct the qubit, because they instead of overlapping at the right point, they overlap at the wrong point. And that means you can reconstruct only with certain fidelity. So that's what is happening. So this is so for a given shift error, you can also show that there is a bound. So if you can squeeze your same encoding, if you squeeze it below this localization length, then also this deletion is impossible, or fast deletion is impossible. So this is very surprising, because you can, but here you are going from one quantum equilibrium state to another non-trivial quantum equilibrium state. So here you have to use the full power of Barnardus to Barnardus transitions. And then you can, so you see that the graphs are not very good, because here you have to do a little bit of numerics to find intersection points. And but definitely these are correct. And so currently what we are also studying what protects against errors if they're generated by small local quenches instead of like these global shifts and all. So this is something that we are also investigating. And all these results are applicable for a system near a critical point, provided these are true, that the quench or the eraser has to be faster than any microscopic timescale. So if you read a Cardi paper, they make these 3 points often, that suppose you take some Ising model or something, whether all these results are valid there, all that you need to do is to make the quench to faster than any microscopic timescale. And the initial and final temperature should be smaller than the cutoff energy scales, where the CFT description is no longer valid. And then the critical point is described by CFT, because we are using holography with a large central charge and a sparse spectrum, or it is strongly interacting here. So if these 3 conditions are satisfied, it will be applicable for reality. So that basically ends the results. And now I just simply end with a summary and outlook. So summary, I think I don't need, because I'll skip that. So just so that I can finish in 5 minutes. So let me explain, ask some questions and see how you can do this. So this is a question that Shiraz was asking. How do these results generalize when the transitions errors happen over a finite interval of time? So I think Shiraz asked a very great question. So normally you won't see that, or so I don't know whether, yeah, we have to find the answer to this question. So you would expect that if the transitions are happening over a finite interval of time, you will still find such non-trivial upper lower bounds, say on transit or irreversible entropy production. And similarly, some kind of protection against erasure, but this will either shift upwards, downwards, I don't know. But it will depend on, so if it's very, very adiabatic, you expect BCTI to be exactly 0. You won't expect any protection. It's extremely small. But if it's non-adiabatic, there could be something. And this is something that we should understand better. And currently, I don't have a very good answer how to. But what we can tell you is that we have been able to generalize this cut and glue method to address the situation. But this can be generalized provided your metric takes this particular form and like this form that I showed earlier. And this may not be the kind of metric Shiraz and Shantani had computed with this kind of forms. It's not maybe the forms that Shiraz and Shantani would get. But if it is of this form, then you can generalize the cut and glue and with this kind of Ball system, and you can answer this question. So, but it remains to be seen in a better way. Either by using analytic methods or by using numerical techniques, we would like to answer this question. So what happens for a relevant or irrelevant deformation? So it's good to ask what happens. So this is something that we can do with TT bar currently. So you can also think of constraining the probability, because as I told earlier, the delta irreversible is actually so what we constrain is expectation value, right? But actually you can have a distribution. And as I said, you can go to the quantum case where you're coupling an evaporating black hole to a reservoir. I'll talk about this soon. So in that case, actually, this actually becomes a fluctuating function, a fluctuating random variable. And then you can see what constraints this. So whether you can put bounds on the moments of this also. And probably you need to also look into some generalization of the usual QNEC called Renyi QNEC. So it's simply the same statement of the QNEC, but instead of entanglement entropy, use Renyi entropy. And this was postulated by Nimal Ashkari recently and has been checked for free field theories in some nice papers. So the question is, can we also investigate fault-tolerant quantum gates? Just like we saw that there's a possibility of fault-tolerant quantum memory. You can also see whether you can construct fault-tolerant quantum gates. And one way to see this is to understand implementing a 2-qubit gate with tolerance against multiple faults by using wormholes with 2 sides. This is something that we are trying to implement and also study whether some of these constructions can give you fault-tolerant quantum 2-qubit gates. So, but we also expect some new insights into quantum gravity. So what kind of quantum engines channels are possible by coupling evaporating black holes with a reservoir? And this is a very generic question that you can ask. They repeat the same kind of analysis in this context, but you're now evolving the black hole and the system together in a self-consistent way. And to answer this question, we'll need to compute not the root Takanagi surface or root Takanagi geodesic, but rather the EW, the Engelhart wall quantum extremal geodesic or extremal surface to answer this question. And what you expect is that you should give new insights into which types of reconstruction of islands are possible, because any kind of reconstruction program can be understood a quantum channel that is decoding the Hawking radiation that is escaping into the reservoir. So we can ask whether such a thing is physically possible. This is something that we are looking into actually with Suresh and his student also, and together all of us. And if possible, then how much resources like time, energy, number of gates is necessary if this is at all possible. So these kind of questions are very deep. I think it goes at the heart of like recent advances into quantum understanding bulk reconstruction. And also we expect that you can get new understanding of black hole dynamics, such as black hole entangled by wormholes. So from such kind of things. So in the end, I just want to say that there's a very beautiful poem by Pablo Neruda. It simply tells you that death arrives very subtly. It arrives all the sound and you cannot hear it. But then if you are very, very careful, you can really see it. So essentially what we are trying to understand here is that quantum gravity is very hard, and to see there are many toy models that tells you how like there are many toy models in the market now which tells you how information is recovered, blah blah blah, and all of that. But the question is, can all these toy models be physical, or which are actually telling you some truth that you can trust? And so for that, maybe you need much subtle techniques, and the quantum null energy condition could be just one of them, but you can also have some Renyi you can have much more stringent. So you need very, very general and robust principles that you should need to apply to see how much of everything you can trust, and or to get some physical answers. Just like you saw that apparently you would think about any kind of entropy increase is possible, but that was made impossible because of the quantum energy condition. So it could be like this. So essentially, just like to understand the footprint of depth, you have to be very, very careful about understanding the footprints of quantum gravity and from toy models. So I think this is the basic lessons I hope hopefully from this talk. So thanks for your attention, and I now wait for questions.
Let's thank Ayan for the nice talk.
So maybe I stop sharing because I can see some more people. Yeah, so please let me know questions if any.
Sorry, I just had a question, maybe as much to Onkar as to you. Onkar's question, I was wondering whether Onkar was suggesting that in the first part of the talk that the QNEC inequality without the S prime squared term might be correct, even though the QNEC equality with the S prime squared term might not be correct.
Yeah, that's right. That's what I was suggesting.
And can you tell us a little bit about the status of these equalities? I mean, are they proved? No.
My understanding is that the one without the S prime squared term has been proved. At least, I mean, there's a general proof of these, the T plus plus greater than S double prime, that kind of inequality, based on tools from algebraic quantum field theory and so on. So actually in 2D CFTs, I'm not, or 2D QFTs, I'm not sure about the status of the proof for the S prime squared term. And
yeah, it is proved. It is proved by Balakrishnan. So Faulkner had a proof exactly using half modular. Yeah. So the half modular inclusions, they were able to prove using tools of algebraic quantum field theory. It should be true for any pointer invariant. But with the S prime squared term, actually it has been proved by Balakrishnan, Faulkner, Kantker, and Wong in 2019. So it has been proved using various tools of OPs and all. It's very non-intuitive proof again. It's not a very simple.
Right. Yeah. So in that paper also, I don't remember very well now, but I don't remember the status of the S prime squared term. But you say that in that paper they already proved this in 2D.
They proved it, and it has been also proved with that S prime squared for holographic 2D CFTs also.
Okay, then what I was saying is clearly not the resolution. Cool.
If there are no further questions,
I just wanted to make one clarificatory thing that Ayan very kindly credited me with some result on the growth of entanglement entropy, but I should say that the original result was derived by Calabrese and Kadi in terms of conformal field theory and by Hartmann and Maldacena. What we did was to generalize those things to charge the systems. So just a small clarification.
Oh, thanks. Yeah, I didn't know that the Hartmann-Maldacena paper had this very general result, like for arbitrary initial and final states.
Okay, I mean it can very easily be adapted to that thing.
Okay. Yeah.
Right.
Great. Thanks.
Okay, let's thank Ayan again.
Thanks. It was a pleasure. Have a nice day.
Thanks.